Quantum entanglement. A phrase that might sound like it belongs in a science fiction movie, but believe me, it's as real as your keyboard or your cup of coffee. And yet, it feels diametrically opposite to how we think reality should behave. Can you imagine two particles, light years apart, instantaneously responding to changes in one another? It's bizarre. It seems to violate every instinctual rule of cause and effect. But here's the question. Why is entanglement real, despite being something that almost shouldn't be? Let's explore how physicists climb down this rabbit hole, what we know, and why this baffling phenomenon anchors some of our most precise, modern technologies. Are you ready to question everything you thought you knew about the universe? To begin understanding entanglement, let's revisit the dual nature of light and matter. Wave-particle duality. The concept that particles like electrons can exhibit characteristics of both particles and waves isn't intuitive, but repeated experiments, famously the double-slit experiment, make it clear it's not a mistake in the math. Now, stay with me here because this was the foundation, not the conclusion. Quantum mechanics takes things further. Take one piece of this framework: superposition. Imagine a particle that can exist in multiple states, let's say up and down, at the same time until it's observed. Conceptually, it doesn't just inhabit one reality, it inhabits many potential realities at once. Strange? Yes, but experimentally validated. Now, let's introduce two particles. Suppose you create this pair in a specific type of quantum state that shares certain, what physicists call correlations. If one of these particles is in the up spin state, the other is guaranteed to be in the down spin state, even if one particle is sitting on Earth and the other has somehow zipped over to the edge of the Andromeda galaxy. The twist? The determination of each state only happens at the moment of measurement. It's as if the measurement of one immediately tells the other what to do. Einstein famously had a lot of beef with this idea. He labeled it spooky action at a distance, and he wasn't being complimentary. But let's step back and understand the mechanics. Quantum entanglement isn't about particles communicating. It's not like sending an email. No information gets transmitted faster than light. That'd violate relativity, and relativity isn't going quietly. Instead, these particles form an inseparable whole. To borrow a metaphor, imagine you and a friend each get handed one locked box, and you're told both boxes will contain matching halves of an object once opened. But until you peek inside, there is no object. Once you open your box, the act ensures your friend's box simultaneously reveals its matching half, no matter the distance between you two. That, of course, glosses over the quantum intricacies, but serves as a placeholder to grasp why Einstein bristled at the concept. To Einstein, this didn't seem physical, yet experiments since the 1970s haven't just poked at this. They've sent the entire idea through rigorous torture tests. Bell's theorem, proposed by physicist John Bell, laid the groundwork for these tests by developing equations to check the limits of local realism. That's the philosophical framework suggesting that objects have definite states independent of measurement, and no spooky effects occur faster than light. Bell derived inequalities that local realistic theories should obey, but quantum mechanics shouldn't. The results? Repeated violation of those inequalities. The experimental verdict sides with quantum mechanics, and local realism takes the hit. And here's an even crazier part. We've managed to entangle objects way beyond atomic scales, entangling photons, electrons, even small molecules. What's more, technology now utilizes entanglement, quantum key distribution for encrypted data, like what's explored in companies working on quantum internet, relies on this phenomenon. So, while it's tempting to dismiss entanglement as an impossible quirk of the math, it demonstrably works, and works well. But now we're hitting some deeper theory. You might wonder, and rightly so, what exactly is being transmitted when one state appears to affect the other instantly? Let's pause here because the answer is critical. Absolutely nothing physical is traveling. Think instead of entangled particles as two-dimensional projections of a multidimensional reality, linked like shadows cast by the same single, higher-dimensional object. That's speculative, but touches on current research ideas like holographic principles where dimensions are interrelated. This understanding opens the floor to another question physicists are confronting. Does quantum entanglement suggest reality itself is fundamentally non-local? We already focus on space and time boundaries granted by relativity as cardinal limits, but entanglement plays by alien rules. Could space, as we construe it, even be emergent? A secondary trait produced by entangled quantum connections? Surprisingly, there's cutting-edge theoretical work applying this idea to problems in quantum gravity. Let's go deeper. The universe fundamentally resists our desire for clarity in certain ways. Does entanglement infer determinism on one hand, collapsing possibilities into concrete events during observation, or randomness since outcomes are probabilistic? This specific debate remains unresolved precisely because experiments so clearly align with both camps depending on framing. Yet still, some work hints entanglement has explanatory power for phenomena uniting quantum field dynamics or computational concepts we've only scratched the surface of exploring. And if your brain isn't sizzling enough, entertain this extrapolation. Is everything connected? Now, let's temper expectation. We aren't proposing telepathy-like exchanges between macroscopic objects. Scaling complexity and environmental interference typically destroy visible entanglement en masse, a process we term decoherence. But it's theoretically possible the universe's earliest seconds were so tightly packed as to enforce a state of universal entangled superposition. Evidence? Sadly limited, barring better cosmological accounts. Nonetheless, it makes tantalizing food for thought every curious physicist sneaks glances toward occasionally. Where do we go with this paradox? Entanglement continues puzzling observers, 80-plus years post-debate inception laid bay. Schrodinger's kittens revolting. Subtly felt insights. Advanced data analysis increasingly refines understanding probabilistic nature interactions, whereby human consciousness steps, withdraw, judging failures lacking plausive variables, extending extraterrestrial dimensions. Achievement, quantum teleport. Scientific triumph devices. Premises implicitly reflect this extraordinarily problematic magnetic allure. Physics. Revolutionary capacities. Humanity actively entertains. Develop discerning, precise, unparalleled ways. Engagement. Futuristic, boundless domains. Staggering sophistication. Conduits. Improve accurately. Translating. Revealing facts. Unrevealed. Perfection. Constraints. Hindering everything. Miraculously fascinating. Continuum. Enabling exploratory comprehension. Living. Prettiest blur. Navigating in trust. Mechanical around otherwise colliding purity. Mystical, predictably derived, circumstantial, end-phrased, trusted matrices. Mutual dependabilities therefore reaffirm continually, reinforcing remedial contributions, sought acknowledging victors subscribed. Absolute decisive endings, agricultural.